Hello everyone, this is the last example on torque. So in this problem, the figure shows a safe hanging by a rope from a boom that consists of uniform hinged beam and a horizontal cable. So for letter A, we are to find the tension in the cable. And for letter B, we are to find the magnitude of the force on the net force on the beam from the hinge. Okay, so we follow the same steps. First, we identify the forces acting on our object. So we have a tension from our cable. We have the weight of the hanging safe. Let's call that W sub M. We have the weight due to the center of mass. And we have the force on the hinge. Let's call that F. Okay, so next we choose a pivot. So we choose our pivot to be at the hinge. So let's call this A. Okay, now let's identify. So this is an extra step. Let's call it 2.1. Identify the effective forces. Okay, so for example, at TC, the effective force is only TC sine of theta. For W sub M, the effective force is only this component. So let's try to analyze. If this is theta, this will have a component of theta. So this will be Wm cosine of theta. So what are the other effective forces? So we have a perpendicular force here. If this is theta, this is W sub capital M cosine of theta. Okay, so on the green colors, we have our effective forces. Okay, so number 3, let's identify the torques along A. Okay, let me draw just the effective forces. So this is W sub capital M cosine of theta. This is TC sine of theta, and this is W sub M cosine of theta. Okay, so all these forces cause a net torque of 0. Okay, so 0 equals, now this component of force causes a rotation about A in this direction. So this will have a negative torque. So we say that this is WCM cosine theta times the lever arm. Now in this problem, the lever arm is not given. We are only given the dimensions A and B. So we may use a simple trigonometric trick. So we have A here and B. This is length A squared plus B squared. Okay, so we know that sine of theta is equal to opposite the angle theta over the hypotenuse. So we may say that A squared plus B squared equals A over sine theta. So similarly, we may say that square root of A squared plus B squared equals B over cosine of theta. But what is A square root of A squared plus B squared? That is the length of our beam. So if you can see in the problem, this is square root of A squared plus B squared. So half the length of our beam would be the moment arm for this force. And we also know that A squared plus B squared, square root of A squared plus B squared can be expressed in terms of sines or cosines. So having that information, we can simplify the cosines and sines. So our moment arm in this case would be, we would choose B over 2 since half of the length times cosine of theta. So we have 1/2 because that's half of A squared plus B squared, and B cosine theta because that is A squared plus B squared. Okay, next we have this force. So it will also have a negative torque. So this is W sub m cosine theta times the moment arm of B cosine theta, since it has the full length. And then lastly, we have this torque to be rotating in this direction. So this will have a positive sign. So this is plus TC sine of theta times moment arm of A over sine of theta. So using our trigonometric values, we can cancel out cosine and sine. So putting in the values, we have 0 equals minus 85 kilograms, which is the weight, which is the mass of the beam, times G times B, 1/2 muna, times B, which is 2.5 meters, minus the mass of the safe for 30 kilograms times G times 1 times length of B again, 2.5 meters, and then lastly plus tension on cable times A, which is 1.9 meters. So solving for TC, we get 6,092.76 newtons. Okay, so that is TC. For letter B, let's find the magnitude F of the net force on the beam from the hinge. So this force F actually can be broken down into vertical and horizontal components. So let's call that Fy and Fx. So to solve for the magnitude of F, we use this vector resolution, the magnitude of the vector resolution. So using Newton's first law, we first solve for the summation of forces on X. This should be the net force. Okay, so along X, we only have this component of force and this component of force to balance out. So we have 0 equals this Fx component from the hinge. This is not the net force Fx. Sorry for the redundant notations. So Fx minus Tc. So these two forces balance out. So we get that Fx equals Tc, which is 6,092.76 newtons. Okay, now for Fy, we have three forces that balance out. This force, and this force. So we have Fy. Again, this is the y component of our F from the wall minus center of mass minus weight of safe. So we have Fy to be 85 kilograms times 9.8 meters per second square plus 430 kilograms times 9.8 meters per second square. So our Fy is 5,047 newtons. Okay, so the magnitude of our force now is square root of Fx squared plus Fy squared. Squared plus 5,047 newtons squared. So this is 7,911.63 newtons.